Hello, Year 12. Right, the photoelectric effect again. Okay, if you remember from last week, this is the piece of kit that I demonstrated to you. It's the gold leaf electroscope. When you've got it charged, the gold leaf goes up. You've got a negatively charged zinc plate. Now, only UV light can discharge it because only ultraviolet or anything with a higher frequency than ultraviolet, each photon has enough energy for the electrons to escape, okay, to escape the zinc atoms in the surface of the zinc plate. Okay, so it's all about the work function of the zinc plate. Now, if you remember the potential well model, it's called, I gave you last lesson, and that's where if we think of a zinc atom as basically a well or a bucket with electrons in it. Now, the electrons closest to the nucleus are at the bottom, and then the electrons will fill up like that. Okay. Now, it's these electrons, these are the ones which are the easiest to remove because they have the shortest energy gap to overcome. And it's this energy gap here which is called the work function. Okay, so let's just draw that in. So the top level, so that amount of energy is the work function, the Greek letter phi. Okay, now if we have visible light coming in, let's say, there you go, red, a visible photon is not going to have enough energy to overcome the work function. In this case, HF is less than phi. However, we saw with zinc that it is UV. Because UV has a higher frequency, there's enough energy in each photon to overcome the work function. Okay. Now, in reality, electrons are emitted with a range, or can be emitted with a range of kinetic energies. Okay, because if the UV photon has enough energy for this electron to overcome its energy jump, then it will be released with some kinetic energy, but that's going to be less than the kinetic energy for the electrons on the top row. Okay, because it all comes down to our photoelectric equation, doesn't it? Which, if you remember, is this one here. So that's the total energy you start with. That's the photon energy that goes in. Now, some of that goes or is left over as kinetic energy, and some is to overcome the work function. But this equation is only this is the case for the top row only. Okay. For the next row down, the energy gap is bigger than the work function. Therefore, there's less kinetic energy left. So in reality, electrons are actually emitted with a range of kinetic energies. Okay, the ones underneath the second row down will be emitted with less kinetic energy than the top row because of this conservation of energy we're looking at in the photoelectric equation. Okay, right. So there's another slide. This is just looking at, this is the potential well model, but it's for a single electron. This is like looking at an electron in its own little well. Okay, there's the energy gap. Okay, let's say this looks like, because it says work function here, this looks like this is an electron in the outer shell. So the red photon, there's not enough. The electron will absorb the red photon, but then it'll fall back down and re-emit the red photon. A green photon gets it just to the top, but then it'll fall back down again and re-emit the green photon. but it's the UV, the high energy UV, that allows it to escape with some kinetic energy. Now, how do we measure the photoelectric effect? Okay, these amounts of kinetic energy are impossible to measure for an electron. You can't set up some light gates and measure the speed at which electrons are emitted at. It's just an impossible task. So we need to think about another way of measuring the kinetic energy of the electrons that are emitted. And it's this thing here. It's called a photocell. Okay, it's quite simple, really. All you need is, so this is your plate. Now this can be, like, it could be zinc, because that's the metal we've looked at so far. And then we've got incoming radiation. Okay, now if the frequency is high enough, then electrons are emitted from the plate, and they're collected on the other side with the collector. Okay, and we can measure the current, because this will produce a complete circuit. Now we've got electrons going over to that side, then we've got a complete circuit, and we can measure the current in that circuit. Okay, so incoming radiation, incoming photons cause electrons to be emitted, and then we've got a complete circuit then, haven't we? Okay, now shows it a little bit better here. If we turn the battery around, okay, say we had the battery like this, where that was the negative terminal. Say we turned it round and made this the negative terminal and made the collector negative. What's the negative charge on the collector going to do to these electrons? Okay, you'd be right if you thought that they're going to repel them. They're going to try and push these electrons back to the metal emitter. Okay, now if we turn the voltage up here to just the right value, just the right amount of potential difference, the electrons will be just stopping short of the collector. And show that this one looks slightly better. Okay, so here we have, okay, there's our battery. We've reversed it. We've got a rheostat, because that's going to enable us to change the potential difference between the anode or emitter and the cathode or collector. But as we can see, we've got our photons coming in, we've got our incident light. It's causing the photoelectric effect in this plate. Electrons are being emitted off with all a different range of kinetic energies. They're being collected at the cathode. But if we turn this potential difference up, then electrons will be pushed back again. The electrons will be pushed back again. Okay, they'll lose their kinetic energy, and then they'll speed up back to the anode again. Now, this is the very clever bit. If we turn this voltage up slowly until the current just reaches zero, that means that the fastest electron is just slowing down, stopping, and then going back again. Okay. Now, why is that useful? Okay. Any ideas? Well, if we know the stopping potential, if we know the potential difference that's required to stop the fastest electron, we can work out how much kinetic energy it has. Let me explain. What's the most important equation from electricity? Okay, anyone go for this one? Anyone go for this one? It's the defining equation for voltage. Yeah, work done per unit of charge. Now, if we rearrange this, we've got work done equals charge times voltage. Now, if the fastest electron, okay, let's say this one here, this is the fastest. This is one from the top row in the zinc atoms. This is emitted. Now, if that passes through this potential difference and just stops and then goes back again, then we can use this equation. Okay. Now, this amount of work done is the amount of kinetic energy removed from that electron. So let's carry on with the equation. So this amount of work done is the kinetic energy of the fastest electrons. Okay, let just try that again. Now that's equal to the charge on an electron, which is E, multiplied by that voltage, which we call the stopping potential, V subscript S. So there we have it, a very, very important relationship, because that enables us to measure the exact kinetic energy of the fastest electrons by just measuring that value of stopping potential. Okay, so there you have it. That's the photo cell and how it's used to actually measure the stopping potential. Right, any questions, please let me know. I shall see you in the next video. Thank you very much.